Relative motion in two dimensions at right angles. Example 1. An Olympic canoeist capable of traveling at a speed of 4.5 meters per second in still water is crossing a river that is flowing with a velocity of 3.2 meters per second east. The river is 2.2 times 10 to the exponent 2 meters wide. Question A. If the canoe is aimed northward, as in the diagram, which we'll see shortly, what is its velocity relative to the shore? How long does the crossing take? Where is the landing position of the canoe relative to its starting position? If the canoe landed directly across from the starting position, at what angle would the canoe have been aimed? For this, we're going to use subscript C for canoe, S for shore, and W for water. So we will have the velocity of the canoe in water and the velocity of the water related to the shore. So here's our diagram. We have the canoe going north. We have the water, the current, flowing at a 90-degree angle to the canoe. And so we have the resultant vector. So we see that the water, the current, has pushed the canoe. Since the unknown is v for the canoe to the shore, we'll use the relative velocity equation. So we know that the velocity of the canoe to the shore is equal to the velocity of the canoe in water plus the velocity of the water relative to the shore, which was 4.5 meters per second north and 3.2 meters per second east. To find the actual value, we will apply the law of Pythagoras. So the velocity is the square root of 4.5 meters per second squared plus 3.2 meters per second squared, which works out to be 5.5 meters per second squared. But we were also asked to find the angle. So we know we have opposite over adjacent, which is the tan of theta. So the inverse tan would be 3.2 divided by 4.5, which is 35 degrees. So we know the velocity of the canoe relative to the shore is 5.5 meters per second going in 35 degrees east of north. Now, part B. To determine the time to cross the river, we consider only the motion perpendicular to the river. So the change in distance is 2.2 times 10 to the exponent 2 meters north. The velocity of the canoe in water is 4.5 meters per second north. So we want to know the time. Well, we have the relationship that velocity is equal to change in distance divided by change in time. So we're going to apply this to find the velocity of the canoe in water. So the change in time is 2.2 times 10 to the exponent 2 meters north divided by 4.5 meters per second north, which works out to be 49 seconds. So it's going to take 49 seconds to cross the river. Now, number C. The current carries the canoe eastward downstream during the time it takes to cross the river. To calculate the downstream displacement, we're going to find the change in distance this time, and using the same formula, the change in distance is equal to the change in velocity of the water relative to the shore times change in time, which we found out. So 3.2 meters per second east times 49 seconds is 1.6 times 10 to the exponent 2 meters east. So this means that the landing position is 2.2 times 10 to the exponent 2 meters north and 1.6 times 10 to the exponent 2 meters east of the starting position. So we can then apply the law of Pythagoras and trigonometry to calculate the resultant displacement to be 2.7 times 10 to the exponent 2 meters, 36 east of north. The last one. So the velocity of the canoe relative to the water has a magnitude of 4.5 meters per second, and it's the hypotenuse of triangle in this figure. The resultant velocity of the vector of the current of the canoe relative to the shore must point directly north for the canoe to land directly north of the starting point. The angle then is the inverse sine, which is opposite over hypotenuse, the velocity of the water relative to the shore, divided by the velocity of the current relative to water, the canoe relative to water, which is the inverse sine of 3.2 meters per second, divided by 4.5 meters per second, giving us theta as 45 degrees. So the canoe must start out on a heading of 45 degrees west of north. Now,